Okay, so let's do the second hour of this session 4. What I want to run through during that second hour is just a multipole expansion, which is something that I presume you'll remember from your first course. We'll try to maybe do it in a slightly more detailed fashion here. So what's the idea? Well, the idea is that you might have a complicated distribution of charges, but if you look at the electrostatic potential from a certain distance away from these charges, then it can simplify. So here are your charges, and here's your observation point, right? So that's you looking at the charges here. And of course, there's a lot of detail in the distribution of these charges here, but from a certain distance, it's kind of difficult for you to notice the whole microscopic structure here. First thing that you would say is that, okay, if I put a ball around here and don't look at the details, then really, in a first approximation, I can just say that the total charge here is a bit like a point charge containing the total charge inside this distribution here. So that would be the monopole term. But then the higher terms are going to allow you to recharacterize the distribution more accurately. So how does it go? Well, the idea is thus to have a kind of approximation scheme for the electrostatic potential viewed from a large distance. Okay, so what's the idea? The idea is that we will need to approximate the core spatial dependence that we have in the formula for the electrostatic potential, which is just 1 over the distance. So here what I'm considering is a point charge at position Rs and an observation point at a certain R which is far away. Now for simplicity, what I'll do here is I'll put the observation point on the z-axis at distance r, and I'll also put the source on the z-axis at position rs. Right, so what does this mean? It means that I can just rewrite this 1 over r minus rs as the following thing. It's just really literally now 1 over r minus rs, and I can rewrite this in a convenient series. So I extract the 1 over r, I'm left with just this ratio here, rs over r, and this here I can expand in the Taylor series. Sorry. And what do I get? I get 1 over r, the sum from L is equal to 0 to infinity, of just rs over r to the power L. Okay, so here we assume that rs over r, absolute value, is less than 1. Okay, so the series converges. So I'm kind of putting myself away from further away than the source is. Okay, now what's the idea here? The idea is that we're essentially writing an expansion for our potential. Now, we've got a problem with a complete azimuthal symmetry because I've got my origin, I've got my rs, and I'll have my r here. Okay, so this thing, if I were to use spherical coordinates with the z-axis, well, like I do here, z-axis going through here, this problem would have azimuthal symmetry. Okay, so we can look at general solution. So general solution of Laplace that we had written last time, by which I mean this one here. And you see, we are now in a situation where we've got azimuthal symmetry, so then this works. We are actually putting our charges on the z-axis, an observation point on the z-axis, so the angle that we're considering is just theta is equal to 0. So this is 1, and we know that the Legendre polynomials evaluated at 1 are equal to 1. So essentially, you see, I have these coefficients here that I'm trying to match. And directly by matching this formula here with what we just wrote down, we can identify the BL coefficient as being just r S to the power L. All right, so direct identification gives that the coefficient BL is equal to R factor RS to the power L. Okay? Now, if we were to put back an arbitrary angle, this would mean that what we would be able to write is that the vector in that case R minus RS, that would just be the same summations we've been doing, L0 to infinity, with now our coefficient BL, which is RS to the power L. And we've got the spatial dependence R to the L plus 1, because these are the B terms in our generic solution. But now, for a generic angle theta, I just have the Legendre polynomial of the cosine of theta, where theta is the angle between R and RS. Okay, so cos theta is really R hat, unit vector direction R, dotted into RS hat. Okay? And again, here we assume that the expansion works. Well, we don't assume, we know that the expansion works if the source is closer to the origin than the observation point. Okay, just so the series converges. Right, so that's kind of a good first step. Now, this is for a point charge at RS, right? If we write now the effective potential that we get from a distribution of charges, we just need to reintegrate over our distribution of source charges. So let's assume that I'm in, I've got a three-dimensional distribution characterized by density rho. So for source charge distribution, rho of vector RS, what we can write immediately is that V at the position R is going to be 1 over 4 pi epsilon 0. The integral over, well, let me write the summation first, maybe. Cleaner. So summation over all these different terms here, L is equal to 0 to infinity of the spatial part 1 over R to the power L plus 1 times the integral over the volume over which rho is non-zero. So V is kind of a packet of charges with distribution rho. So I integrate my volume element into that, and I have the vector RS, absolute value, to the power L. And then I have the Legendre polynomial of cos theta, which is just R hat dotted into R source hat, times the distribution rho at rho source. Okay, so this is the kind of so this is, if you want, the multipole expansion for arbitrary rho. And for a distance which is greater than any source charge distance from the origin. Okay, so like this for any rho S in the volume V. Okay, so this is quite an important formula. right? It's the thing that you can always refer to when you've got a generic situation with multipoles. All right, so maybe just some very simple examples on this. Again, these are things that you probably already know. So let's just do the simple case of an electric dipole. So in the case of a dipole, what I'm going to do is I'm going to take charges plus or minus q, and I'm going to put them at plus or minus some vector d, okay, over 2. Okay, so this plus q minus q, and this vector here is just d. Okay, so origin is here, plus or minus d over 2. Right. In that case, my v of r is just going to be the sum of the 2 point source potentials that I already know, 1 over r minus d over 2, okay, minus 1 over r plus d over 2. Okay, and now let theta be the angle between r and d. Okay. In that case, if I look at r plus or minus d over 2, really I'm just doing the this dotted into this, right? So this is going to be this dot into that, which is r squared, and then this dotted into that, which is d over 2 squared. Okay, and then I've got the just the rd, so plus or minus rd cos theta. Okay. Actually, I should write minus or plus here. And this I can just write as r squared times 1 minus or plus d over r cos theta plus d squared over 4r squared. Okay, that's the exact expression here. Now if I take that r is much bigger than d, I can approximate this. If I look at r minus d over 2, this is like 1 over r with 1 plus or minus d over r cos theta, because I'm in the denominator. Okay, and then to the 1/2, and this is like 1 over r times 1 plus or minus d over 2r cos theta. Right? So we get, if we use this formula here with then the other formula for the change sign here, so we get that v of r is now approximately equal to 1 over 4 pi epsilon 0, but now I have q times d cos theta divided by r squared. Okay, so a couple of comments. You see, that kind of makes sense. If I'm far away from these two charges, I would have a first dominant term which would be corresponding to the sum of the two charges. That vanishes. So the 1 over r term in the potential, the leading term, vanishes because this dipole has a total charge of 0. But then, as if I was doing a 1 over r expansion, the next first non-zero term would be the 1 over r squared term. So the dipole term here falls off faster than the kind of basic point charge contribution. Now, the idea is that this is completely general, right? So here I've done a very simple dipole, okay? You know, term by term. We have a certain nomenclature for the expansion of the potential that we have, okay? So we have the monopole term, V mono of R, which is 1 over 4 pi epsilon 0 Q over R, where Q is just the total charge. So it's going to be the integral over your volume of source charges, just the density of the charges. The next term is the dipole term. And the dipole term looks like this. So you have the dipole R, again 1 over 4 pi epsilon 0. Now I have a 1 over r squared, and I have an integral over the volume of my source charges, but now I should put the first Legendre polynomial, right? I'm looking at this. So this is the first Legendre polynomial. I've got the L is equal to 1 term here, and we know that the first Legendre polynomial of x is just x. I wrote that somewhere yesterday. Well, actually, an hour ago for you. But I don't find it anymore. Okay, so so here I would just have the r source absolute value, and then just r hat dotted into r source hat, and this coming from P1 of r dot rs. Okay, hats. With just the row of rs. But you see, I can rewrite that a little bit because the norm of rs times rs hat is just really rs. So I can simplify the notations a little bit. The dipole term here is going to be 1 over 4 pi epsilon 0 with now r hat dotted into a vector p that we'll just define in a second, all that divided by r squared, where p is by definition the integral over your volume distribution of charges, of source charges, d tau s, of rs times rho of rs. Okay, and this is called the dipole moment. Okay, so you already know how that goes. Okay, so of course we don't have to stop there, right? We can also carry on. So another rather typical is the next one. okay, which is the quadrupole term. Okay, the quadrupole term is this object. So I've got the quad of R. What am I doing? I'm just taking the next term in the series that we were writing here. So I'm now at L is equal to 2. Okay, so what is this? 1 over 4 pi epsilon 0. Now I've got a 1 over R cubed integral over my volume d tau source of Rs squared, right? So this is just the length of the vector. And now I have the P2, the second Legendre polynomial of R hat dotted into Rs hat with the row of Rs. Okay, so we know that P2 of x, again, this is something that I wrote. Let me try to find it again for you. So I wrote them at the bottom of the page somewhere. Yeah, here, you see, so P2 is just a half 3x squared minus 1. Okay. P2 of x is 1 half with 3x squared minus 1. So what we can do is rewrite this quadrupole term as 1 over 4 pi epsilon 0 with now 1 half factor here. The summation over a b is equal to xyz. Of RA, RB over R to the 5 now. Yeah, you see, so it goes like 1 over R cubed now, 1 more power of R overall, with an object QAB, which is called the quadrupole moment. QAB is equal to integral over V of your source charges of 3 R source component A, R source component B, minus the length squared with Kronecker delta of A and B. Okay, all of this times your charge density at the source, row source. Okay, so it's a symmetric function. It's a symmetric tensor because A and B, the indices can be exchanged and it doesn't matter. It's a rank 2 object, right? And it's traceless. Yeah, so if you do summation over A of QAA, it's going to give you 0. Okay, so it has 5 independent components. You'd think it was 6, but because of the traceless condition, 1 falls off. Okay, so in all its kind of practical glory, we have our beautiful approximation for the electrostatic potential of a source charge distribution, 1 over 4 pi epsilon 0, with, what do we have? We have the monopole term, Q over R. We have the dipole term, so sum over A of RA PA over R cubed. Right, so you see this goes like 1 over R squared, and then we have plus 1 half sum over AB of RA RB over R5, right? So this is in total a 1 over distance cubed, QAB, plus blah, blah, blah. Okay, we could carry on until kingdom come here to whatever order we'd want. If the quadrupole term is not accurate enough for us, we can just go to the other ones. Now there's a fun little info box in the notes about the nomenclature that is used here, and I kind of complained that physicists messed up a bit here because they mixed Greek and Latin. You can have fun deciding for yourself whether you prefer the Latin or the Greek in here. Okay, so that's the general idea of the multipole expansion. In the notes, there's a little bit about the electric field of a dipole. Yeah, maybe I'll have I'll just tell you this in a couple of seconds. So the electric field of a dipole. Well, what do we have? We have that the potential of a dipole for a certain r is 1 over 4 pi epsilon 0 with p cos theta over r squared, where cos theta is once again the angle between the observation point and the dipole. So if we take the gradient, we can compute what that is. So the gradient, again, I refer to the gradients that we have here. When we take the gradient of the potential, we get the electric field. So ER is equal to minus dV dr. So this is 1 over 4 pi epsilon 0 2p cos theta over r cubed. If we have the E theta is minus 1 over r dv d theta. I'm using the notations for the gradient in spherical coordinates. 1 over 4 pi epsilon 0 p sine theta over r cubed, and the E phi, which is minus 1 over r sine theta dv d phi. This is just 0. Okay, so what we get is that the electric field coming from a dipole, if we're sitting at coordinates r theta and spherical coordinates, this is just 1 over 4 pi epsilon 0 p over r cubed with 2 cos theta r hat plus sine theta theta hat. Okay, and as an exercise, you can show that in a coordinate-free notation, you would get that E of a dipole, yeah, that's E from the dipole, at r is equal to 1 over 4 pi epsilon 0, 1 over r cubed, with now 3 times the dipole moment with r hat in the direction of r hat minus the dipole moment, like this. Okay, and you can just plug in your favorite coordinate system and verify that this is correct. So this is the proper way of writing it up if you want. Okay, so the general idea here is that from this point onwards, each time I give you a certain charge distribution in space and ask you to tell me what it looks like from a certain distance, you should jump on this formula here and start computing the monopole term, the dipole moment, the quadrupole moment if you need it, okay, with the knowledge that the further away you are, the lesser the higher order terms are important as compared to the original ones. So typically in a problem, what you would do is you would look at the the situation, and you'd fish out the first non-zero term here, and that would give you a sufficiently accurate approximation that you could then complement with other terms if you needed them. Okay, so in some of the problems that you'll get, you'll have to compute these moments here. But the idea is quite simple. Once again, this is stuff that you should have seen before, so I hope it's just a little bit clearer than it was, or that it is simply refreshed in your memory as compared to what you've already seen. Okay, so that's it. We will put the exercises online a little bit later this week on Tuesday or Wednesday, and I'll see you people next week. Thank you very much.